We're going to start this section with a review of polar coordinates. You probably saw polar coordinates in your trigonometry class, but it's good to take a moment to review the basics. Polar coordinates is a coordinate system set up around circles that are centered at the origin. Locations in this coordinate system are denoted by a pair of values r, theta. The r value corresponds to the distance from the origin, and theta is the angle to that point as measured from the positive x-axis. So the point 3 pi over 4 is on the circle of radius 3 at an angle pi over 4. We can relate points in polar coordinates to points in rectangular coordinates using right triangle trigonometry. If we start with a point xy in rectangular coordinates, we can use that point to draw a right triangle. We can then label the length of the legs of the triangle. This allows us to calculate r by using the Pythagorean theorem. The angle at the origin is theta, and we can set up an equation to get its value using the tangent function. Conversion in the other direction is also an exercise in right triangle trigonometry. The same diagram gives us the formula x equals r cosine theta and y equals r sine theta. It's important to note that theta is not uniquely defined, as you can increase the angle by 2 pi and end up in the same location. This allows us to continuously wrap around the origin instead of having a discontinuous jump in the angle from 2 pi all the way back down to 0. The big idea is that we want to be able to integrate using polar coordinates. This is useful because some integrals are more circular than rectangular, and so it is helpful to be able to use a more natural coordinate system. In fact, some integrals are impossible to do unless they're done in the appropriate coordinate system. The basic integral can still be set up as a double integral using the area element dA, but we can no longer use dx dy to represent that because that corresponds to rectangular coordinates. Instead, we need to use a polar rectangle, which are the shapes that we create when we draw the lines of constant r and theta. However, it's not quite as easy as just using dr d theta. The problem is that you can have the same values for dr and d theta and end up with two different areas. This is because the area also depends on how far from the origin you are. So we will need to figure out how to compensate for that. The trick is to think about the geometry of the situation. The space between the two radii creates an annulus, which is a washer-shaped region. The space between the angles is what gives us the polar rectangle. Activity 11.5.3 walks through the process of calculating that area, and then taking the limit as the r and theta values get very close to each other. The end result is that you get dA is equal to r dr d theta, and that area element gives us what we need to convert everything into polar coordinates. Here's the formula for the double integral in polar coordinates. This feels complicated, but all it's saying is that you substitute r cosine theta for x, r sine theta for y, and r dr d theta for dA. And then you need to set up your limits and integrate. Setting up the integrals can be tricky because you're probably not as familiar with polar graphs. For the d theta integral, most problems are simply going to have constants, and so that tends to be easy. For the dr integral, you're trying to trace from the lower curve to the upper curve, where the curves are functions of the form r equals something in terms of theta. In the r direction, you can think of lower to upper as inner to outer, tracing outward from the origin. You may need to sketch the polar graph to figure out which is which, but once you've done that, it's no different than in rectangular coordinates. When doing these problems, it's helpful to remember the Pythagorean identity. This will be useful when making substitutions. The most prominent example comes from the expression x squared plus y squared. In fact, in general situations, when you see the combination x squared plus y squared, that is sometimes a hint that you may want to think about using polar coordinates instead of rectangular coordinates. This gives you the basic groundwork for working with integrals in polar coordinates. As with so many other things in calculus, you're going to need to invest some time working through problems to get comfortable with it. The book has both activities and exercises to guide your practice.